Okay, here we go. Last lesson in redox and electrochemistry. Um, we're moving away from the battery and we're going to move on to the electrochemical cells where reactions happen that are driven by the battery. Reactions that the battery makes happen. That's why these are referred to as non-spontaneous. The battery by itself will have a reaction that creates electrical power. We don't have to do anything to it. It is spontaneous. These reactions require a battery. These are the endothermic ones. They're non-spontaneous because they require energy to be provided for the reactions to progress in the forward direction, or at least the forward direction that we would like to see. They would actually reverse themselves spontaneously, but that's not the reaction that we want to see happen. Okay, so these are either electrolytic or electroplating. All the workings of these two types of reactions are pretty much the same. Um, there are slight differences in terms of what happens. They are the same in terms of the charges and directions of electron flow and non-spontaneous, negative calculated voltages, all these other things that we'll discuss. They are the same. I'm still going to write this. Red, cat, on, and ox. It's reduction, cathode, anode oxidation, but this time the cathode is negative and the anode is positive. That's because when we connect the negative of the battery, we connect anode to cathode. But in the battery, the anode is negative. We're connecting it to the cathode and making that cathode negative, forcing it to be negative, right? Pushing the electron. The battery is an electron pump, like your heart pumps blood around your body. The battery pumps electrons through a system. The electrons come out of the anode of the battery. That anode is negative because of the surplus of electrons there. And then those electrons transfer to the next electrode, which is the cathode, because we go anode back to cathode in the direction of our electron flow. And you'll see that in the diagram that I show you. I'm thinking realistically I should probably do this as two separate lessons. To do it at one might be too much. I might do the electrolytic and electroplating cell separately. I think I'm going to start with the electroplating cell because that's actually the easier one to do. All right, and I'll show you how that works. There's our battery with the positive and negative charge. Just like I showed you, inside here we have an oxidation, a reduction. Where the reduction is going to be the cathode. Where the oxidation is, that's going to be the anode. There's some sort of a paste in there or some sort of a membrane that acts like the salt bridge for the ion migration. And the electrons are flowing through what they refer to as the external circuit, where we have our anode and our cathode. Okay, out of this one, and it goes around to the other one and back into this one. It's out of the negative and into the positive with respect to the battery. The battery provides the direction of electron flow. I'm going to do the electroplating cell. I think I'm going to do the electroplating cell today only because in the electroplating cell, it's a little easier because there really is no net reaction. No reaction occurs. Because what we're doing is moving metal. We're moving it through a chemical process, but there's no chemical change because we're taking a metal that's on one electrode and putting it onto another one. I think when I gave the introduction overview to this lesson, I think I drew the electroplating of like a ring. I either silver or gold plated the ring depending on whatever I made the anode to be. That's the one that kind of dissolves and transfers over. So I think I'm going to do the same thing. I'm going to gold plated ring and then just give you the reactions this time. Because the reactions in the electrolytic and electroplating cell are the harder ones for you to get because now you actually have to deal with half reactions, net ionic change if there is. Today there is no net ionic change. Tomorrow, well, next lesson I guess it'll be Monday. Monday's lesson there will be a net ionic change. Okay, so let's go ahead and look at this. Going to draw my beaker where my reaction is going to be. I'm going to make my ring. And now I'm going to make this gold because I'm going to put gold on my ring. That's kind of a fat ring. It looks more like a donut. But that's my ring. Now, this is going to oxidize, right? The gold is going to go away. It's going to become gold ions, go into the solution, and then migrate over to the donut. I mean the ring. Migrate over to the ring, and that ring is going to get plated in gold. So this is the one that I need to be negative, because plating occurs at the negative. I'm going to write that down. Plating is at the negative, which is the cathode. Plating occurs at the cathode, which is negative in the electroplating cell. Not the battery, that's the opposite, but here, the metal is going to be reduced. Okay, so I'm going to connect my wire. I guess I got to put an electrode on this, connect a wire to this, and a wire to that. Remember, this is the battery, this is the negative terminal, so electrons are coming out. Electrons are going over here, right? So when the electrons travel out of the battery, they go onto the ring. Guess what? That ring gets electrons stuck on it. So this ring becomes negative. There's all little electrons on that ring. Okay? Now, the electrons go into the positive. So my electrons travel out of here. So the battery's pumping them, right? Because the total number of electrons have to remain constant. They're coming out of the negative. For every one that leaves the negative, one has to go back into the positive. Okay? So they're being pumped around. Since this is becoming negative, this is becoming positive, right? Now check this out. When this becomes positive, when I have gold, hopefully I left myself enough room here to write my half reactions. You know what? I'm going to do it on top of the page so you can see it. If I start writing on the bottom, you might not be able to see clearly. So let me write on top. Okay. I'm going to write what's happening at the cathode, okay? The cathode, electrons are being pulled out. So I have a piece of gold metal here that's losing electrons. Losing electrons, oxidation. Losing electrons, oxidation. The gold is going to oxidize. So what's going to happen to the charge? It's got to go up. So I'm going to go AU, currently at 0, that's this, is going to lose electrons, and gold forms a positive 3 ion. You know what? It can form 1 or 3. The more common one is positive 3. If you're ever asked to write a half reaction, as long as you write an appropriate charge, it would be fine. Like for gold, since gold has choices of 1 or 3, you could use 1 or 3. If you were doing calcium, the oxidation of calcium, if you wrote calcium positive 4, that would be wrong because calcium is a group 2 metal, and group 2 are only going to be positive 2, right? We got to remember our rules, okay? And those charges are also given on the periodic table for the ones you don't know or the more common ones. So use one of the charges on the periodic table. Now, we're going to balance this for mass and charge, okay? Well, mass is the same. Since this has 3 electrons, this is the higher side. 3 electrons got to go here, just like we learned previously, same thing. Plus 3e negative. So what does that mean to my little solution here? Remember, this is sitting in a water solution. Not a water solution, but an electrolyte solution. Probably a gold nitrate or some nitrate solution that's conductive. If you try doing it in pure water, you won't get any conduction in here. So if you don't get conduction, then no reaction is going to happen. You got to complete the circuit. So as we said before, water doesn't conduct electricity. It's the ions in water. So they have to put some sort of a solution. It might even do nitric acid. I don't know. But there would have to be some sort of solution in here to conduct the electricity. So anyhow, gold ions in nitrates are soluble. So this is going to dissolve. And you're going to get Au positive 3. That's a U, folks. Au positive 3. You got gold ions in the solution, right? And that's what we have going on here, right? So this is actually going to get smaller. It's going to wither away. We're transferring mass. That's why this electroplating cell, it is an electrochemical reaction, but there is no net chemical change. Metal from here just transfers here. It's almost as if, look, I have my marker here, I pick my marker up and put it here. That's not a chemical change. It's a physical change. So technically this is physical. This is a physical change by chemical means because it's two opposing chemical reactions. Now let's look at this side. This is my ring that became negative. This gold ion that I put into the solution is positive. Where do you think the positive is going to go? Duh. Opposites attract. Positives go to negative. This is going to go over here. There are extra electrons to here. So this is going to gain those electrons. Gaining electrons, what's going to happen there? Reduction. That's why it's the cathode. So the electrons are going to go onto the gold ion. The gold ion is then going to stick to the ring, take those electrons, which causes more electrons to be transferred over. It keeps going until all the metal is transferred or the energy in the battery becomes gone. The chemicals in the battery get used up. They all get moved over through the salt bridge medium, and then it's done. So now I'm going to write the half reaction for the other side. The gold ion, the Au positive 3, is going to become gold metal on the ring. That's at 0. And now we got to put the electrons in. Same rule before. Side of higher charge, same number. Okay. And that represents our two half reactions. Now, why do I say that this is really nothing in terms of a chemical change? Let me show you. There's something that we call net ionic reaction. It's the summation of the oxidation and the reduction. When we write those net ionic changes, we want the number of electrons to equal 0. So we're going to sum these. Oh my God, here we go. It's the math here. Ready, folks? We're going to sum these in the same way that we sum polynomial expressions. That means we pick one term that we'd like to cancel out. The term that we'd like to cancel out are the electrons. That means in these expressions, we're going to multiply one reaction or the other by whatever number we need to multiply it by to get the number of electrons the same. Right? So this has 3, this has 3. So for this one, it's actually easy because the number of electrons are the same. In all electroplating reactions, it's going to be like that because the metal that you're oxidizing is the same as the metal that you're reducing. So the number of electrons in each half reaction is the same. Tomorrow's lesson, I'll be able to go through it a little bit faster. And I'll give you a couple of examples of the reactions that happen because that'll be a little more confusing in the electrolytic. But you're going to see that we're going to have to multiply one reaction or the other to get the number of electrons to cancel. It's not that tricky. It sounds trickier than it is, but for today, it's much more straightforward. The number of electrons are going to be the same. So we're just going to add our expressions. Okay. Now, we're going to add the expressions. All right. And we're going to get Au positive 3 plus Au plus 3e negative equals Au positive 3 plus Au plus 3e negative. Everything we have on the left side and right side is the same, which means there is no net chemical change, right? No reaction. Because remember, when you have a polynomial expression, things that are on opposite sides that are the same would cancel. So Au3 here would cancel with Au3 here. Au here cancels with Au here. 3 electrons here, 3 electrons there. So, although I have these two half reactions, all right, I'm going to get rid of this line too. There is no net ionic change. Tomorrow you're going to see a net ionic change. Okay? So this represents our electroplating reaction. Watch it again, take some notes on it. You will be getting, I guess I'm going to have to find some practice questions for you. Maybe Tuesday or Wednesday I'll post them and then review them the following week. I got to figure out a good schedule for next week so I can get you some useful work and then try and schedule it in on the days that we have our Zoom meeting so I can discuss them with you. But that's pretty it. pretty much it. Have a good day today. You get some time between your classes. I don't know how much work you have. It's going to be really nice out today. Tomorrow's going to be a little warm and sticky. Today's going to be another nice day to get outside, enjoy the air, get out into your backyards. Don't go to the parks, or if you do go to a park, social distance, that type of thing. Okay? Me and, hey, say hi. Hey, say hi. Me and Phoenix over here bid you a fond adieu. Have a good day, guys. Bye-bye.